400 hertz, 589.99, 1185.8. Three numbers, three separate measurements, taken decades apart by researchers who never worked together, all describing the same thing: the exact frequencies at which centuries-old stained glass starts to move. Not metaphorically, not vibrates with meaning, measured in hertz with accelerometers and laser sensors, on some of the oldest surviving glass in Europe. Not a legend, not a restorer's folk wisdom passed down in a workshop. A facsimile window panel, 1100 by 650 millimeters, built by the cathedral's own restoration team to match the original glass exactly, mounted on an electrodynamic shaker in a laboratory, and driven deliberately at the frequencies a bell or a crowd might actually produce. The panel's dimensions matched, the lead came pattern matched, the glass thickness matched the historical record down to the millimeter. Whoever ran this test wanted to know precisely what 400 years of bells had actually been doing to the windows above their heads. I spent the next few months trying to find out who had asked this question before, and what they'd found. Milan, then Wales, then a modeling lab whose exact location the papers don't name, running the same physics on a computer instead of a shaker table. 3 different research efforts, 3 different decades, 3 different methods, the same underlying question, the same stubborn set of numbers. You can explain one study measuring glass vibration as a coincidence of funding. You can explain 2 if you're generous about shared engineering training. You can explain a small cluster if you accept enough coincidence. But at some point, the coincidences stop behaving like coincidences. At some point, the pattern itself becomes the evidence. History remembers progress. It tends to forget what it replaced. Once you see it, you can't unsee it. If the weight of this story has reached you, if the feeling that something was deliberately forgotten has settled somewhere, consider leaving a mark before we continue. A like costs nothing. A subscription costs nothing. But both tell us that the archive still matters, that the contradictions still matter. Stay with us. There is more to uncover. But to understand what was truly erased, we have to return to where the record ends. 1386. Construction begins on the Duomo di Milano. 6 centuries later, it is still, technically, unfinished. A cathedral that has never stopped being a construction site, in one sense or another. Somewhere in the last decade, engineers from the Politecnico di Milano, working with the Veneranda Fabbrica del Duomo, the historic body that has managed the cathedral's fabric for over 600 years, installed something the original builders never imagined: seismometers. 14 of them mounted at the top of selected piers. 3 more on the main spire. Tilt meters. Extensometers on the iron tie rods holding the structure together. 6 years of continuous data, not a single dramatic reading. A slow, patient record of how an 800-year-old stone skeleton actually moves. Day after day, season after season. The official purpose is straightforward: structural health monitoring, catching small problems before they become collapses. This is true. It is also incomplete, because buried inside that same research program is a stranger, more specific question. Not just how the stone moves, how the glass does. Cold marble underfoot, incense and machine oil mixing in a nave that is simultaneously a place of worship and an active engineering site. Cable runs taped along a 13th century floor. A sensor, no larger than a coin, glued to the inside of a window frame that has held color since before the printing press existed. The cathedral's oldest surviving glass dates to the 15th and 16th centuries. It has survived fire, war, and 400 years of bells ringing directly above it. Nobody, until recently, had actually measured what that ringing does. You can't put an accelerometer on a 15th century window and hope for the best, so the researchers built a copy instead. 1100 millimeters by 650, the exact dimensions of a real panel from the cathedral's facade. Built by the cathedral's own restorers, using the same lead cam pattern, the same glass thickness, the same jointing technique masons and glaziers have used on this building for centuries. Then they mounted it on an electrodynamic shaker and drove it, deliberately, at frequencies matching real bells and real crowds, the kind of sound pressure a concert in the square outside the cathedral actually produces. 400 hertz, that number. Measure, in a separate but related experiment on window glass more broadly, as the frequency at which resonance peaks, the sweet spot where sound and glass start moving together instead of past each other. A three-dimensional vision system tracked the panel's movement in real time, catching deformation too small for the eye to see. The official concern going in was simple. Does sound break glass? The answer that came back was more specific and more interesting. It doesn't, not directly. What breaks, slowly, over years, is the lead. The soft metal cames holding each piece of glass in place fatigue under repeated vibration, loosen, and let the glass panels rattle against their own frame. The damage isn't a shattering, it's a slow, mechanical loosening, glass chattering in a socket that used to hold it firm. And the cathedral's own facade, it turns out, was already protected by something nobody had designed for this purpose. An outer layer of glazing, added generations ago for weatherproofing, happens to sit between the ancient windows and the open square, filtering out most of the vibration before it ever reaches the original glass. An accident of maintenance, doing the job of a laboratory-grade buffer. Wales, the Cathedral of St. David's, at the far southwestern tip of Britain. 1969, Concorde, the supersonic airliner, in its early test flights, was producing sonic booms across the British countryside. And somewhere in the Ministry of Aviation, someone asked an obvious, overlooked question. What happens to old buildings when a jet breaks the sound barrier overhead? A researcher named F.L. Hunt, working for the Royal Aircraft Establishment, was sent to find out. He measured vibration amplitudes directly inside St. David's Cathedral during actual Concorde test flights. Real sonic bangs, real instruments, real 13th century stonework and glass shaking under a kind of acoustic stress no medieval builder ever accounted for. The official concern was aviation policy. Could supersonic flight paths be approved without risking Britain's historic buildings? This is true. It is also incomplete because Hunt's data became something larger, one of the earliest rigorous data sets on how a real cathedral responds to a sudden, sharp acoustic shock. Not a controlled laboratory hum, but an actual, unrepeatable sonic event. A separate study, published the same year by A.J. Pretlove in the Journal of Sound and Vibration, modeled the same underlying physics, how large windows respond, elastically, to sonic bang pressure waves, using mathematics rather than a cathedral roof. 1969. Hunt measures St. David's directly. 1969. Hunt publishes again, refining the same data. Decades later, Milan runs the same question on a shaker table instead of a jet. Different countries, different decades, different sound sources, a supersonic aircraft, a concert crowd, a bell. The same underlying question asked by researchers who, very likely, never read each other's work. What does sound actually do to the glass that has outlived every person who ever installed it? A shaker table needs a real panel. A sonic boom needs a real cathedral and a very expensive aircraft. A finite element model needs neither. A separate line of research, mechanical engineers building computer simulations of stained glass under acoustic load, pushed the question further than any physical test easily could. Working entirely in software, they modeled how a bell's acoustic wave propagates through the air, strikes a glass panel, and sets it vibrating at its own natural frequencies. 589.99 hertz, 1185.8, 1413.9, 1773.8, 2376.5. Each number is a distinct mode of vibration, a different pattern in which the same sheet of glass can move, layered on top of each other, the way a struck bell rings with more than one note at once. I am not claiming that any single research team working in isolation deliberately withheld a unified theory of how bells damage stained glass. I am asking something more uncomfortable than that. I am asking whether this kind of knowledge, scattered across aviation ministries, cathedral engineering offices, and mechanical engineering labs that rarely read each other's journals, can exist in genuine, rigorous pieces for decades, without anyone assembling it into a single, complete picture. Here is where this stops being distant. If you have ever stood near a large church bell while it rang, close enough to feel the sound in your chest rather than just hear it with your ears, you were standing inside the same physical event these researchers spent careers measuring. The windows above you were moving. You almost certainly never knew by how much. I went back to Milan on an ordinary afternoon. No concert in the square. Tourists moved through the nave in loose clusters, necks craned toward glass that has held color since before Columbus sailed. Somewhere above their heads, sensors smaller than a coin were still recording, silently, the way they do every hour of every day, whether or not anyone below knows they're there. A bell rang for the hour. Nobody flinched, nobody looked up. Above them, glass that has survived 6 centuries moved by a fraction no eye could catch. Exactly the amount 3 separate research efforts on 2 continents across half a century had each measured in their own way. Why did it take until the last few decades for anyone to actually measure what centuries of bells were doing to the glass above them? Why do 3 independent studies, a sonic boom test in Wales, a shaker table experiment in Milan, a computer model built by engineers who study neither cathedrals nor bells for a living, keep landing on the same physical behavior? Why does the real danger turn out to be the quiet fatigue of soft lead rather than the dramatic shattering everyone assumed? Who decided that question wasn't worth asking sooner? By the 3rd generation after a piece of knowledge stops being asked about, the fact that anyone ever needed to ask it starts to sound less like engineering and more like trivia. And I find myself wondering whether we're already there. The ones for whom centuries of bells ringing directly above irreplaceable glass never once prompted the obvious question, until a handful of researchers, working in isolation, finally did. I keep coming back to the same question, and I still don't have a full answer for it. Not why the question took so long to ask. Not even why the answer, once found, stayed so scattered across separate fields that rarely speak to each other. But this: how many other quiet, measurable things are still ringing, unrecorded, above heads that never think to look up? The glass listens. We rarely do. If something in this account stayed with you, a number that repeated across decades, a study that came close and moved on, a question nobody thought to connect, find the oldest record you can, the oldest measurement, the oldest test, the oldest report filed and forgotten. Look at what the numbers tell you that no single study said on its own. Then tell us what you find. Leave it in the comments. The most important contradictions are often the ones carried in silence. And if you choose to subscribe, you are choosing to continue looking. The archive is not finished. Under this video, you'll see a thanks button, a small gesture with a big meaning. By pressing it, you're not only supporting the creation of more content like this, but you're also becoming part of the very exchange we've been talking about, giving and receiving in harmony. It's not about the size of the gesture, it's about the meaning. A simple super thanks tells me these words reached you. It tells me that the effort, the late nights, and the discipline to bring this message forward mattered to someone on the other side of the screen.